Okay, we start up. So today we are going to continue with Turbulence and open foam. So I'm going to mess around with some tutorials and change them and play around with them, and hopefully we will make it work. Now, you had been given the exercise number 2, and I know there are some problems here, like executing these commands. Sadly, open foam changes its version and it changes its notation every year, and it's different whether you use org or cum version. Welcome to life. That's how it is. So you have to struggle with it. Now, sadly, the version I have, well, I can make it work for me, but I have an older version, and that's not so good. I've tried to install the latest one, but my PC couldn't handle it. I have to find another machine, because I would like to have the sort of the latest version, the same as you have. That would be a little bit more easier. That said, I mean, these commands, especially the first one, is quite important. And exercise 2 is important. So, let us just do the following. We edit exercise 2, and then we just change the deadline. Because it is important, trust me. Due date, where are we? Friday the 13th. Ooh, that's a bad omen. Let's do that. Then you have another week on that one. Any questions before we start? Yeah.
Were the exercises obligatory to do?
No, I mean, the exercises is not mandatory, meaning I'm not going to check that you have done the exercises. I don't have to, as long as you have done your 5 exercise reports, so I can give you a grade. If you haven't done any of these, then it's very easy for me to give you a grade. Your choice. No, but you don't have to deliver the exercises. So you can do it if you like. Then you have the access to them for years to come also. That's also a point. But no. Also, I would like to give you a solution, both exercise 1 and exercise 2, before we start with the first, say, report exercise. Any other questions? Okie doke. Then let's get started here. Yeah, I will continue where I left off the last time. I have downloaded the Pitch Daily case. I think in some of you maybe it's called Pitch Daily Steady, I think. So, but you should be able to find it. When you want to find something, we can take that one. Find, where to search, and then you write $, big letters, foam, underscore, tutorials, and then you say -type, and then you type in either directory or a file. We can try a directory, -name, and then pitch daily. And then you should achieve a list under your tutorials where you can find all the different Pitch Daily cases. So I want to start with a simple foam. That's the easiest one. Pitch Daily. Piso and Pimple. Well, here we have a large eddy simulation. Thank you very much. Stay away from that one. The Pimple foam, that's an Reynolds averaged stress model. So that one might be okay, but it's pitch daily, no sorry, pimple foam. I wonder if it may be transient as well. Never mind. Start with the simple foam. Please interrupt me here if you have any questions. I am now in my pitch daily case and I have the minimum setup. So let's just run it blindly first. Block mesh. And we can check the mesh as well. I mean, from these standard tutorials, it shouldn't be necessary to check the mesh, but I mean, it's nice. It's a nice habit. You should always do that, actually. And then no problem here. And then we can run. I have to write simple foam. Some of you may have to write something like foam run or something, so it always changes. Foam run, that's sort of an umbrella for letting the system find out which program actually to run. It should be simple foam though. So we find the solution within 281 iterations. Okay, so I've got some result folders, and remember this is a steady state setup. It's only the last one that is of interest. He stops automatically when all the residuals are small enough. And you see he has now solved for K and epsilon. Aha, turbulence, yes. And the overall residual looks nice and small. Shouldn't be any problem here. And just to have a look at it, para foam. And let's try one thing first. It should be possible, if you're lucky, if you write para foam minus block. Block, thank you. I don't think it works on my version. No, you didn't understand that one. Not defined. But if it works, you will get up the graphics, the mesh, but then with different block structure. I mean, how has he created the mesh with different blocks, and each block will have its own color. So it's a nice overview, if you can make it work. I can't make it work on my version, but I try it. So that's a nice one. Okay, that was minus block. Because the mesh here in this tutorial is not the easiest mesh. So let's just click apply here. We can have a look at the mesh. Just only look at wireframe and a solid color. And when you want to look at the mesh, then I will recommend you to switch on camera parallel projection. Then you get rid of this 3D effect. I mean, it's only a two-dimensional mesh, but the 3D effect will distort the view a lot. So here, if we now zoom in, for instance, say somewhere here, then you can see the mesh, say close to the step. Quite nice and smooth. A little bit of jump here in size. That's not so good. The mesh should be smooth and look nicely. You shouldn't have too much change in area from one cell to the neighbor cell. But I think he can handle this one. It shouldn't be too hard. And the mesh, how it is constructed, we can have a look at it later. Let's go back to surface, thank you, and then have a look at the velocity. And yeah, we discussed this one the last time. The steady state solution, yeah, you have one big vortex after the step, and then you have a nozzle and the outflow. Let's have a look at some of these turbulent quantities. They should be automatically uploaded here, depending on which turbulence model you have chosen. So let's start with the turbulent kinetic energy. It looks something like this. And if you look at the numbers here, it's not that big, 5.5. Does that make sense? we are sending in 10 meters per second. That's the bulk velocity coming in at the outlet, at the inlet. So this K, that would then be, say, a turbulent velocity on average, actually squared. So he shouldn't be bigger than your inlet value, of course, or the bulk velocity. Depending on the Reynolds number, he may be quite big. I mean, 5.5 is not that small compared to 10 meters per second. But he shouldn't be too small either. Well, if you have a very low Reynolds number, close to laminar, well, he's going to disappear. He's going to be 0 or close. So that's not good. One important thing here, we are sending in something here at the inlet. Have a look at that later. We have to give a value for K. Now, there you have to sort of find an estimate for what should that number be. And yeah, you find several recipes of these, either in the user guide in OpenFOAM or the Turbulence file I gave you last time. It should be out on the homepage. So you can find a way to calculate or give an estimate of this K here. And then when you do a simulation, then you check if you have put in a way too big number here, then you will see something coming in here, and then you won't see anything else. And what you send in is going to die out quite rapidly. Then you have a way too big number. The value at the inlet is way too high. The other way, if you send in too small value, then you'll hardly see anything. I mean, the turbulence is sort of killed before you even begin. So you have a look at these plots. Not that they necessarily say so much. Why is K biggest here? Well, why not? I mean, you produce the turbulence typically alongside the walls, especially around this step here, and then it's transported and then catched inside this vortex. So yeah, should make sense. But have a look at the inlet values, that they don't overshadow the entire domain, or yeah, is totally crazy. Same goes with the epsilon. Quite intense somewhere here. And the number here, whoa, is big one, 5,700, thank you. But I mean, we don't have any law relation with epsilon. We don't know how big this number should be. But again, we have to send in a number, and then if you send in a too big one, then he will overshadow everything. Too small, then the turbulence will die. So you have to sort of check the plot that that the inlet doesn't kill your entire simulation. We even have the eddy viscosity, and well, he's quite small actually for this turbulence model. Let's have a look at the inlet file here. I see now we have under our 0 folder a whole bunch of files. Because this setup for Pitts Daily has been done with the possibility of choosing different turbulence models. I can show you. First of all, let's clean out this result folders. Foam list times minus remove. Sort of a good idea every time you are going to change something and simulate again, so you don't have a mix of different result folders from different cases. That's you're going to be schizophrenic. So let's start with looking at the file in the constant folder that has something to do with turbulence. In my version, it's called turbulence properties. I wonder if normally you guys, you have something in momentum something. Anyhow, you should be able to find it. It's not that many files here anyway. So let's have a look at this file. And here looks something like this. Simulation type, Reynolds averaged stress model. And the model we have chosen is K epsilon. But here you see it's been tested with, and then you have a whole bunch of different models. So it's a nice tutorial that you can play around with different turbulence models and see the different effects. And also, if you are wondering what model is accessible, you use the banana trick. It's a very good trick. You write something stupid here, and then you say that one, and then you try to run it. So let's try that one. Simple form. I don't have to recreate the mesh. I only change the model. The mesh is the same. So yes, you get an error, total crash, and then you have a list valid models. So this banana trick is quite nice in open form. When you are wondering what's my options, write banana or some stupid word, and then you try to run it. He will crash, but probably, hopefully, then give you a list over possible entries that you can use. So yes, here I have 21 models. Okay, let us undo that one. I'll just keep K epsilon, that's okay. Let's have a look at the different files in this case here. Let's start with the mesh. And the mesh, well, first of all, you see you have a scale here. So every number is divided by 1000. So that's not so nice. And also must be some Americans that has done this. 25.4 divided by 1000, that's 2.5 centimeters, that's 1 inch. So sadly, but never mind. So yes, you have a whole bunch of corners, define some values here, and then you have several blocks. And how these are organized, that's my point, where you could have help from this parafoam minus block. Then you could see the different blocks, how they are organized. They have some simple grading and some edge grading. So the meshes, they are not uniform, they are stretched a little bit in the different directions here. Coming back to that one later. And then further down here, we have some boundaries, inlet, outlet, upper wall, lower wall. I mean, these names, you can call them whatever you want, but they have to match the same name in then the different zero files. Show you later. And also we have front and back, hence, yes, it's a two-dimensional case. So let's have a look at some of these zero files. Velocity. Okay, I send in, as you can see at the inlet here, 10 meters per second in the x direction. Okay, outlet, I have no idea, hence zero gradient. Here you have a Dirichlet condition, you give a number. Here you have a Neumann condition, you give a derivative equal to 0. Upper wall, lower wall, just no slip. You could also here use the fixed value 0, 0, 0. That will be the same. And front and back is empty. Now, while we're here, let's have a look at the Reynolds number. The opening, I think that's roughly 1 inch. And we have now a velocity scale of 10. Okay? Then the only thing we need is the viscosity. Where do we find the viscosity? Constant, and then the transport properties. Okay, so it's 10 to the power of minus 5. So we have 10 multiplied with 100,000, that's 1 million. And then we multiply with 0.025. So yeah, it's highly turbulent, clearly. If you want to change the Reynolds number, I would suggest you change the viscosity. That's the easy way, instead of have to create new meshes, everything. Okay, then let's have a look at some of these other files here. What about the K? Well, first of all, they have set the entire field for K to a number, and they give a constant number in. Not that big, 0.3. What was the biggest K? That was 5.5 or something like that. So the inlet value is quite low actually compared to what we find in our solution. Outlet, no idea. And then here, upper wall, lower wall. They use a wall function. This is something we discussed last time. That's important. When should you use a wall function? You should use a wall function if your distance to the nearest cell, or actually to the center of the nearest cell close to the wall, and the y plus distance there is bigger than 30. Then you should use wall function. Else, if it's smaller than 6, then you should use normal boundary conditions here. Just give him a fixed value and then a very small number or 0. Well, actually, I won't recommend 0. Use a very, very small number. 10 to the power of minus 6, 8, 10, something like that. So we have to check after we have done the simulation, is it a match with the wall function or not wall function and the y plus along the walls? We have to have a look at that one. Same goes with the epsilon. Where do we have epsilon? Here. Again, they give here the internal field a value. That might be smart. If you don't do that, you risk then that the turbulence will sort of never start to grow. Here, quite high Reynolds number, we have a quite strong driving force in the system. The turbulence is going to survive here anyway, I think, but it may converge faster. Remember, we are only interested in the steady state to get there as fast as possible, so why not? And here again, the same number at the inlet. So close to 15. Then for the walls, okay, also here used wall functions, meaning y plus should be bigger than 30. Now let's have a look at this y plus thing. I want to find the y plus. Now on my computer I had to write the following. Simple form minus post process, and then it was minus func, if I recall correctly, and then it was y plus with a big P, plus, like that. Let's see if it works. So it did. And then you get a lot of information here. What's important is the two walls. Now remember, for the Pitts-Daly case, you have the bottom wall with the step and the top wall. Well, that's also a solid wall. Not what you are going to do in your exercise 2. You are going to have a symmetry line up in the sky. Here it's a solid wall. Now here, this one I don't get. Upper wall is 0. That must be something wrong. And also look at the lower wall. Maximum is close to 20. On average, it's 14. Very, very bad idea. That's just in the area where you don't want your y plus. Either smaller than 6 or bigger than 30. This is not good. This is not good. And now, when you have received a y plus field, you can actually have a look at it inside Parafoam. So if I now click apply, he should automatically load it. You have a list somewhere. Where is it? Oh, it's gone already. Never mind. He should be here. Let's have a look. We have to run. I have removed my result folder. Sorry. That's why I got so strange results. Come on. Yeah, I forgot to do the simulation. Simple folder. And then let us do this y plus again. Thank you, that was a little bit better. Still, I don't like these numbers. Top wall 14 and 10. Lower wall close to 30, but below, and on average 15. That's just the value you don't want. So now let's have a look at y plus. Let's see. By default, he should choose all your variables that sort of are active in your simulation. So here you see you have everything, U and pressure, and then K epsilon, eddy viscosity, and the y plus. You don't have omega because we don't use the K omega turbulence model. We don't have that. So he should detect it automatically. If something is not checked out, then check it and then click apply. So now we take a look at the latest time and look at y plus. You don't see much because y plus is only calculated alongside the walls, but they are here. Maybe you have to zoom in a little bit. And then also here you have the numbers. So the biggest one is 27. The red color must be somewhere here, I guess. So the other ones, they are not so good. Let's, whoops. Now what happened? He crashed. Okay. Let's try it again. Apply, y plus, and the final time. I want to zoom in here a little bit. Let's have a look at the step. This one is quite crucial. So you see light blue here. Well, it's 10 or below. But is he below 6? Oh, I don't think so. Maybe here, down in the corner. Okay, here he might be small, but here the velocity isn't quite small anyway. So this one is not a problem. This is actually a problem. So the mesh is not good. The mesh is not good. So there you see the mesh here. We can zoom in a little bit more. So, as I say, the y plus value is then given in the cell centers. OpenFOAM is a co-located program, meaning he has put all your variables in the center of each cell. So that's why he sort of has interpolated from 0 here to a value on the wall. So it's on the wall value that is important. I mean, if you use the other y plus here, not the interpolated one, but this one, he will give you a constant value for each cell. Well, then you don't see anything. So you have to use this interpolated value here. So the mesh here, no, it's not good. It's if you want to use warm models, then I would say this mesh is too fine. We should reduce the number of cells. We should have bigger cells alongside the walls. Here we are on the limit. I mean, it's not that far from 20 or 30 down to 6. So it should be possible here to resolve the boundary layer so that we can have more natural boundary conditions. That would be better. How can we simple and easy refine the mesh here? Well, let's try it. First, let's get rid of the old result. Where are we here? That one. remove the result folder, home this time, minus remove. And then we try this command here. Refine wall layer. It's a crude one, actually not to be recommended, but it should be possible to use that one. So refine wall layer, like that. And then you have to use minus overwrite. Minus overwrite meaning he's going to destroy the old mesh and write a new one. Overwrite. And then you have to specify the name of your wall that you want to refine. Let's just take the lower one. I think it was the same, wasn't it? Lower wall. We try. Lower wall. Something like that. And then you have to give him a number. What number? Here I suggested 0.7. That's just an arbitrary number from my side. It should be between 0 and 1. This will give you sort of the percentage. How does he now refine the cell closest to the wall? If you take 0.5, let's do it crudely here. Then he should split the closest cell in half. We try that one. Okay. Overwrite. That was over. Doesn't he have that? Ah, maybe another big W. Overwrite. Thank you. There he has done it. Finished refining. Okay. Let's do it once more. Let's see what happens. Now we have done it twice. Okay. Let's try to simulate anyway. Simple foam. Let's see if we can handle. Well, maybe we should. I think that's a good idea. Run the check mesh. Well, the mesh is still okay. We have some more cells now, but never mind. Let's try to run it. Simple foam. Simple foam. He used 270 iterations this time. Still he managed. Now let's create the Y plus while we're at it. Here we are, the Y plus. Look at the lower wall. Now we're talking 5.6 and 2.8. Now I am below 6. So now I could use normal boundary conditions without wall functions for the turbulent, different turbulent parameters. I haven't done it. We still have wall functions. So the solution here may be a little bit off, but never mind. Let's just have a look at the mesh, what he has done. So let's just take apply. And we have some Y, well, never mind. Let's have a look at just the mesh. Solid color, and then switch on camera parallel projection. Let us zoom in here. Let's see what he has done. There you see it. First cell, closest to the wall, that was the first time, split in half. Then I did it again, so the next one also split in half. Little bit crude. Here you have, say, 100% change in area. That's not so good. So it's a very crude method, but I mean it's cheap, and sometimes it can save the day. And also sometimes you get some strange effects from this refined wall layer. Have a look at the corner up here. What the heck is he doing here? Making some very strange cells. If you overdo this, then here you risk having an area close to 0, and then he won't run. Then the check mesh will fail. So it has to be used with care, this refine wall layer. But since it's such an easy way to do it, it can be worth noticing. So what else should we do here instead of this refine wall layer? Well, we should actually have stretched the mesh a little bit. Let's have a look at how that can be done. Any questions so far? So now I have a better mesh, but now with natural boundary conditions. Hence what I should do, I should edit all these 0 files for K, epsilon, and then I should switch this one into a type fixed value, and then a uniform and a very small number. So this is something you should investigate then for your exercise 2 when you are seeking out finding the reattachment length. So you try either with a coarse mesh, so that you have to use wall functions, and then you can try with a finer mesh, y plus smaller than 6. Then you have natural boundary conditions here, just a constant small number, and see the difference. So that is your job there. Okay, let's get out of that one. Let's see now, we have 5 more minutes. Let's go to the first case that we looked at here. I have the cavity case, square cavity. And here we have a very, very nice mesh. Let's see, block mesh. If you can recall the cavity case, you have one top wall, he's moving with a constant velocity. Then you have 3 fixed walls, and then front and back is a 2D case. And we only have 20 by 20 cells, so it's a quite crude one. But never mind. So here we now have created the mesh. Okay, let's try this refine wall layer on this mesh. I mean, the mesh was uniform here. Refine wall layer, then minus over right, and then we need the name of these walls. Let's choose only the fixed walls. Fixed walls. Like that. And now again, let's do the same. 0.5, 0.5, and then I run it once more. 0.5, 0.5. Okay, let's have a look at the mesh. Wireframe and the parallel projection. So there you see what he has done. It was 20 by 20 uniform, and we have split the closest cell in half, and then that cell also in half. But you look at the corners, they don't look nice. We get some messy things there, I don't like it. Not that it's so important. Down here, you hardly have any velocity at all. So it's not crucial. He won't change the overall solution, I think. Still, I don't like it. Now have a look if I do the same, but now with the moving wall. Moving, it's just one wall, isn't it? Moving wall. That was 1, and that was 2. Now let's have a look at the mesh. So we just apply wireframe and parallel projection. So now we have also stretched towards the top wall. And for this case, this is actually quite crucial. Here is where all the physics happens anyway. So it's quite important to resolve this boundary layer well. But look at how he has handled the small corners up here. Much better than what he does automatically down here. So hence, if you are going to use this refine wall layer, then I will recommend you have top wall, left wall, right wall and bottom, and do them one wall at a time. Then he will handle such corners much, much better, instead of doing something really messy down here. I don't like this, this thing. These are terrible cells. They're really distorted. So no, they are not good. Although here I think he will handle it. It's not that sensitive part of the domain anyway. But just be aware of that one. Any questions? Then after the break I will try to make this one also turbulent. Let's see how that can be done. Then we take a break.